Hi, my name is Abdelmajid Garwet, and today I'm going to present my topic in avionics seminar, which is Rover drive system. The video that you are watching right now was taken from the Mars surface, and it was recorded by the rover Perseverance. Mars has been observed and documented by astronomers for centuries, and as telescope improved, scientists gained a clearer view of Mars, including its polar ice caps and surface features. Mars is a prime target for explorations due to its similarities to Earth, making it a potential place to search for signs of past or present life. Studying Mars helps us understand the history and the evolution of our planet. The best way to have a closer look is by sending rovers to Mars. Rovers are autonomous robotic vehicles designed to traverse Mars terrain. Rovers carry a suite of scientific instruments, including cameras, spectrometers, and drills, enabling them to analyze rocks, soil, and the Martian atmosphere. Plus, rovers can cover a wide range of terrain and access locations that stationary landers cannot, providing a broader prospect on Mars geology and climate. And in this presentation, I'm going to focus on the drive system of the rovers, which includes the motors, the wheels, the suspension system, and the mechanical transmission system. But the greater focus on this presentation is going to be on the motors, as they are the most complicated system and require much more attention and consideration while designing the rover. And we're going to have a closer look also with the overview on the suspension system and the wheels used in the rover missions. And the final part of this presentation, we're going to show some missions, previous missions, and discuss the type of the motors that were used and the drive system. Motor type of rover drive system. When selecting a motor for the drive system, there are several criteria that we should take into consideration. These criteria are low rotor inertia, low mass, high torque, and high positioning accuracy. So if we can consider these criteria carefully, we can see that the low rotor inertia plays a major role in all of them. If the rotor of the motor has low inertia, it means probably that the motor has a lower mass. And it means also that the motor has high torque. Also, if we have high inertia, it means that the control system won't be able to stop the motor at a precise location or a precise angle. So the main focus to have the best performance of the motor for the rover system is to choose or to select motors that include rare earth permanent magnets in their design, because by replacing the electromagnets by rare earth permanent magnets, we can reduce the volume of the motor by 40 up to 70%. And we can increase the efficiency of the motor by 50%. And there are the rare earth permanent magnets can be obtained by mixing different alloys of rare earth elements. And when speaking about space missions, two main types come to surface, and these are the most used type for the space missions, which are the neodymium magnets and the samarium cobalt magnets. The neodymium is the strongest rare earth permanent magnet known, and it has high magnetic density, and it's not very expensive. But the problem with neodymium rare earth permanent magnet is the high temperature. If it's exposed to a temperature higher than 80 degrees, it will lose its magnetic density. And depending on the type of the rover, the planets where the rover is sent, and the thermal isolation system, neodymium still can be used, and it has been used in the previous missions, but in condition to protect it carefully from the high temperature. And if the thermal system is not as efficient to protect the motor from high temperature, the alternative is to use samarium cobalt rare earth permanent magnet, because it can withstand a temperature as high as 200 degrees Celsius. But the problem with the samarium cobalt is it has a lower magnetic density, and it's more expensive in comparison with neodymium. With that being said, we can choose between these four types of motors for our mission, which are the stepper motor, the servo motor, brushed DC motor, and brushless DC motor. All of these motors include rare earth permanent magnet in their design. And the stepper motor has been used in previous missions, but not for the drive system, because servo motor is well known with its high positioning accuracy, and it can be controlled with an open loop control system. It doesn't require closed loop control system. However, with high speed, the stepper motor loses the torque, and this can't be used for this reason. It can't be used for the drive system. The counterpart, which is the servo motor, is it has better performance with the high speed and can maintain its high torque. But the servo motor design is based on the brush DC motor with the compact electronics and small mechanical system. And for space mission, for rover space mission, it's better to use a brush DC motor with the dedicated mechanical design, let's say gearbox or a transmission system, and dedicated electrical design, let's say controller to control the speed and the torque of the motor precisely. That's why we are not going to discuss the servo motors. Instead of that, we're going to directly discuss the brush DC motor, which is the most known and the most used motor for the drive system in the previous rover missions. The brush DC motor has a simple configuration with two wires control, meaning we can control the velocity or the speed of the motor by controlling the voltage at the end of the two wires. And it's ideal for extreme environments due to the lack of electronics. Because later on, we're going to see the brushless DC motor, which has complex electronic, and this can be problematic for the space missions, for the rovers. And the brush DC motor doesn't have any complex electronics, except if we need to control the speed of the motor or the torque of the motor by using a controller, PI controller, for example. We're going to need electronics. But the basic design of the motor doesn't include electronics. And the problem with the brush DC motor, it has a short lifetime because of the brushes. The commutation system in the brush DC motor is based on using carbon graphite brushes to commutate the DC voltage. And the carbon graphite brushes is very efficient on Earth because it requires a layer of humidity and oxygen. And this layer will harden with time and extend the lifetime of the brushes. But this can't be found on Mars surface, for example. And that's why using brush DC motor with the carbon graphite is not possible for the Mars missions, for example. But depending on the lifetime of the mission, it still can be used. The other type of the motors is the brushless DC motor. Brushless DC motor is the most performant motor known so far because it has a longer life. It doesn't include any mechanical commutation system. It has an electrical or complex electronics for the commutation system. And with this complex electronics, we can precisely control the torque of the motor to high level or control the speed of the motor. And by removing the mechanical commutation system, the motor has a lighter weight in comparison to a brush DC motor. But the problem, as said before, the brushless DC motor has this complex electronics, which can be challenging in the space environment because it requires a higher protection. And also, in order to control the brushless DC motor, we need to know the position of the shaft of the motor at any given moment. So we need the sensor feedback from the rotor. And this is done by using Hall effect sensors or an encoder to know the position of the shaft. But this also can be problematic because sensors usually are very sensitive to radiation, and using sensors in space needs extra requirements to protect them. In this slide, we're going to briefly discuss the working principle of brush DC motors. A brush DC motor consists of a rotor, a stator, and a commutator. When current flow through the armature winding, a magnetic field is generated, causing the rotor to rotate. The brushes makes contact with the commutator segment, allowing the current flow to change direction at the right time to enable rotation. The speed of the motor can be controlled by adjusting the voltage. And the spring-loaded carbon graphite brushes, which are shown in the small picture, creates a friction and wear out with usage. And this is in normal Earth condition. But this phenomena is much more extensive in the vacuum because graphite brushes need humidity and oxygen, which is available in the Earth atmosphere. And with the humidity and oxygen, the graphite brushes will build up a hardened patina on the surface of the brushes. In the absence of humidity and oxygen, the brushes will wear very rapidly. And this situation was, with no humidity and oxygen, was noticed during the Viking lander mission, where they used brushed DC motor for the camera system, and they noticed that using carbon graphite brushes isn't efficient in vacuum environments. And there is another phenomena that comes with the brush by using the brushes, which is called sparking. In theory, a brush DC motor can rotate in high speed up to 20,000 RPM, but in reality, a brush DC motor can't exceed 10,000 RPM. And because of the brushes, when the commutator rotates with a high speed higher than 10,000 RPM, the brushes won't conduct the current flow as they're supposed to be, and the current will be lost, and then therefore the limit is 10,000 RPM. Even with the problems that I mentioned with the brush DC motor, it's still the most common solution for the drive system, for the motors for the drive system. And this is mainly because of the solution that were discovered over the years. And there are two main solutions that I'm going to discuss in this presentation, which are precious metal brushes and graphite brushes. The precious metal brushes is a very expensive solution because the metal that they use for the brushes is either gold or silver. And it has the problem of a very limited current flow, but it offers a solution of it offers very low friction and small and constant voltage drop over the commutation system. So we can avoid the problem of the friction by using these precious metal brushes. But the current flow is very low, so it means probably that we're gonna need to that we're gonna have a very small torque on the motor, or we can use, for example, a mechanical transmission system with a high ratio to replace to solve the problem of the small or the low torque. There is another problem with the precious metal brushes, which is the continuous working mode. With this setup, we can't frequently change the direction of rotation of the motor, meaning we either have to stick with the clockwise rotation or counterclockwise rotation. And if we change the direction of the rotation frequently, the system will break very easily. And the second solution is to use graphite brushes. And so the first model was based on carbon graphite brushes, and it's the most common solution on Earth. But for the space mission, there were several experiments to change the carbon graphite with a mixture of different alloys. And the most successful alloy mixture is to use carbon with copper and silver. And even though this solution still has a high friction and still has a high audible noise, but still, if the friction is there but doesn't reduce the lifetime of the motor, it's not a problem, and it has been very successful solution for the Spirit and Opportunity, for example, the Rovers. And with using a mixture of different alloys for the graphite brushes, we still can have a high current flow on the motor, which means that we can have a high torque on the motor shaft. Second type of motors that we're going to discuss today, and it is the most performant motor, it's the brushless DC motor. The brushless DC motor design is similar to the AC synchronous motor, and the main difference between the two is the shape of the back EMF. In the AC synchronous motor, the back EMF has a synchronous shape, while the brushless DC motor, while in the brushless DC motor, the back EMF has trapezoidal shape, the one that you can see in the graph. And the electronic control system monitors the rotor position using the sensor and applies the current to the stator to generate rotation. And with this setup, the motor can reach a speed of 100,000 RPM. But the problem, as I said before, is the Hall effect sensor, because Hall effect sensors that are used in the brushless DC motors are very vulnerable in the radiation. Even though there are several methods on how to control the motor with sensorless feedback, but these methods are not efficient with high speed. And the second problem is the electronic commutation system. It is very complex, and it requires high precision to control the motor efficiently. And it requires also high or extra protection from the space radiation. But on the other hand, the brushless DC motor has very high performance, And maybe the main problem or the thing that can limit the lifetime of the brushless DC motor is the bearing. But the bearing are much easier to understand, and we can predict the lifetime of the bearing much more easier than the brushed used in brushed DC motors. The suspension system, one of the most iconic and widely used suspension systems on the Mars rover, is the Rocker-Bogie. The Rocker-Bogie is highly adaptive design, used on several NASA missions, including Sojourner, Spirit, Opportunity, Curiosity, and Perseverance. It is inspired by a six-wheel vehicle suspension system developed for the Earth-based explorations, but it is modified for the Mars unique challenges. The Rocker-Bogie system consists of two major components, the rocker and the bogie. The rocker is a pivoting structure that connects the rover's body to the wheel on each side. It allows the rover to rock or pivot in response to changes in terrain, keeping the body relatively level. The bogie is a multi-wheel assembly that houses the wheels on each side. It can move up and down independently, ensuring that the wheels maintain contact with the ground on uneven surfaces. The Rocker-Bogie system is incredibly adaptable, allowing the rover to navigate even over obstacles and rough terrain with ease. When a wheel encounters an obstacle, it can move upward independently, while the rest of the rover's body remains relatively stable. This prevents the entire rover from getting stuck or tripping over. This suspension system provides exceptional stability, even if one wheel is hanging in the air. The rover can continue to move forward without tilting excessively. Wheels on the Mars rover have been one of the biggest technical difficulties encountered on the missions, suffering damage from the rough Martian terrain. Even on flat, solid ground, the rover's top speed is just around 0.15 kilometers per hour. Even with this slow pace, it generates enough forces to create holes in the rover's aluminum wheels. Engineers face strict criteria that complicate their task. The wheels have to be strong enough to support the nearly 1-ton rover, yet as lightweight as possible to save on launch cost. And the wheels also need to maintain traction and navigate the unpredictable Martian terrain. The record for the longest journey covered by a rover belongs to the Opportunity rover at 45 kilometers, with the previous record held by the Russian Lunkod 2, a lunar rover. All Mars rovers have used solid aluminum wheels. This design worked for earlier rovers like Sojourner, Opportunity, and Spirit, but the Curiosity rover, with its extra weight, proved to be challenging. Each of the Curiosity wheels is about half a meter in diameter and 400 millimeters wide. They are made from a solid block of aluminum. Several critical design considerations must be respected when it comes to the rover wheels. Material choice is paramount. Mars' harsh, dusty environment, with its extreme temperature, demands wheels made from resilient materials like aluminum or titanium. The size and the shape of the wheels are also very important. Larger wheels can surmount obstacles more efficiently and provide stability, while the unique tread pattern on the wheels are designed to enhance the traction and minimize the slipping on challenging terrain. The last segment of this presentation is dedicated to mention several rover or Mars exploration missions with the emphasis on the type of the motors that were used and with regards to what I have discussed in this video earlier. And the first mission that I'm going to speak about is Viking 1 and 2. And this mission didn't include any rover, but it was essential for the following missions because a considerable amount of motors were used on this mission. And the testing phase was essential for a lot of discoveries about the functionality of motors in the Mars environment and in space in general. And this mission was launched in 1997, and it lasted for 7 years. And three types of motors that were used on this mission, and they are the brushed DC motor, the stepper motor, and the brushless DC motor. The brushed DC motor was used for the sample acquisition system for drilling into the Martian surface to collect soil and rocket samples. The stepper motor was used for the sample handling system to precisely position the robotic arm and its various instruments, allowing accurate sample analysis and experimentations. And the brushless DC motor was used for rotating the camera housing and moving the scanning mirrors. And it was revealed later on after the success of this mission that during the test phase, which started in 1973, that the problems that they were facing with the motors were always on the top 10 problems encountered the team or the crew who built the lander and the orbiter. And the second mission that I'm going to discuss is the Mars Pathfinder. It was launched in 1997 and it lasted only for 3 months. But this mission included a rover, which named Sojourner. And this mission included 11 brushed DC motors with the internal design based on the usage of precious metal brushes instead of the carbon graphite brushes, and with using permanent magnets, rare earth permanent magnet, which is neodymium magnet. And as discussed earlier in this presentation, the precious metal brushes system doesn't allow a high current flow. So to overcome this problem, the design was based on using a gearbox with gearing ratio of 2000 to 1. And this gearbox limited the torque demanded from the motors for the drive system. And the expected wheel load was just 1 Newton meter for the front wheel and 0.5 Newton meter for the rear wheel, and with an overall current flow of maximum 160 milliamps. And there were several modifications made on the motors to be able to function on the Martian surface and the Martian environments. Namely, the structure of the motor was constructed by using titanium and fiber carbon structure to mitigate thermal expansion. And they used the capacitor to limit the sparking phenomena at the level of the brushes. And the total distance covered by this rover was 100 meters. But due to the high gearing ratio, the motor had to rotate over 500,000 rotation for this short distance. And the third mission that I'm going to speak about is none other than the famous Mars exploration mission, Spirit and Opportunity. And Spirit and Opportunity were launched in 2004, and the lifetime of the rover Spirit was until 2010, and for the rover Opportunity was until 2019. And the type of the motors that were used for the drive system for the both rovers was also brushed DC motor, but instead of using precious metal, they used graphite brushes. And graphite brushes allow high current flow. So they didn't have a problem with producing high torque for the drive system. Still, they used a gearing ratio or a gearbox with a gearing ratio of 1500 to 1. And this is a relatively high gearing ratio. And other than this, each rover contained 39 motors for drive and steering system for different applications, such as solar array deployment, camera and actuators, and for the science arm joints. And the maximum load on the wheels was 90 Newton meter with the current flow of 2 amps. And the end of mission of the rover Spirit was in 2010, and this was because of failure of one of the motors of the drive system. And with the design based on using a gearbox of a ratio of 1500 to 1, when one of the motors fails, this will be a blocker, and this will won't allow the rover to move. So it's always a trade-off between using a gearbox with a high ratio and limit the torque of the motor, or using the motor directly with the high torque and high currents without the gearbox.